Very good morning, dear participants. Good evening to the audience who are joining from other part of the globe. I'm Dr. Vishalakshi Prabhu, Assistant Professor in the Department of CSE, RV College of Engineering, Bengaluru, with my students, and Dr. Eshaan, University of Hawaii, are lined up to present our project works. Respected dignitaries from HPCC Systems and LexisNexis Risk Solutions, dear delegates, stakeholders, researchers, developers, and students, a warm welcome to each of you for the breakout session on fueling our success. Today, we will be giving insights into two projects. Let us proceed with the first project work titled Building an NLP Pipeline for Electronic Health Records and Brain MRI Classification. With RBC Bengaluru, we have established a Center of Excellence in Cognitive Intelligence Systems for Sustainable Solutions. Through this COE, several activities like student hackathon, participation in poster presentation, research proposal writing, for executing funded projects are carried out. Many ideas grow better when transplanted into another mind than where they sprang up, by Oliver Wendell. Our current work is result of one such proposal accepted and funded by HPCC Systems for the duration January to December 2024. This presentation highlights the importance of NLP in the analysis of electronic health records, which contains detailed information of medical history of individual patients and the usage of HPCC Systems as a platform to leverage the idea. Medical information is highly unstructured and no suitable format available. Our project helps one in understanding the processing power of HPCC systems when it comes to complex computations with large amounts of medical data. As an extension, we have aimed at enhancing the analysis of brain disease using deep learning techniques. This innovative project focuses on the classification of brain disease through MRI scans, leveraging the powerful HPCC Systems platform. By utilizing the pre-trained VGG16 model for image recognition, HPCC Systems' robust processing capabilities, our work demonstrates the handling of huge brain image datasets and performing complex computations. This approach not only aids medical professionals in making accurate diagnostic decisions, it also helps healthcare professionals for the impactful healthcare solutions. Objectives. The motive behind the project is to create an integrated system capable of handling real-time medical information extracted from the electronic health records of patients with the brain disorder. We make use of these medical entities to further predict that whether a patient needs an MRI scan or not. In case after obtaining an MRI scan, the system allows for the upload of the scan, which it provides a precise classification of the brain disease from a predefined set of categories. Project is designed in such a way to assist both patients and medical professionals. It helps patients gauge the severity of their condition, and it aids the doctors in taking a suitable decision based on the EHRs and MRI data. The development of a web-based application ensures an interactive and user-friendly navigation for seamless access to these capabilities. Coming to the methodology, our project has solution in two parts. First, natural language processing for electronic health records. Second, deep learning for brain MRI classification. Over to Eshaan Mathur, student of second year CSE, for further discussion on NLP-based methodology for medical data.
Greetings to one and all. My name is Eshaan Mathur, and I'm from second year Computer Science Engineering, RV College of Engineering. I will be explaining the methodology behind the project. First, I'll start with explaining the methodology of the NLP part of our project. This part itself was divided into two phases. So the first phase basically involved us extracting medical entities from various medical texts which we had with us. The target entities which we extracted included the gender of the person, the symptoms experienced by the person, the duration for which each of these symptoms lasted for, as well as the organs that were affected. The data which we used for this particular task, it was basically the EHR data from various hospitals in Bengaluru and the PMC patients dataset, which was a dataset consisting of patient details of about 167,000 patients. The labeling of the data was performed with the help of a pre-trained model using biomedical NER, which was already trained, and we made use of it along with a few more pre-processing to label the data set which we had. The word embeddings which we had used in this particular project were generated using BioBERT, which was deployed locally on the HPCC Systems cluster. The BioSTM CRF architecture was employed for the particular task of named entity recognition in our case. When we trained the model finally, the BioSTM CRF architecture, we achieved an overall accuracy of 98.6%. The next task, after we were able to extract the medical entities, was to decide as to whether a person has to proceed for an MRI or not. The biggest features, which, as I just mentioned, the gender, symptoms, duration, and the affected organs, were represented in the form of a graphical representation. For each and every patient, a graph was constructed, and the final output which we expected from this was to decide whether a patient has to proceed for an MRI or not. A simple classification task. So after this, we basically made use of the graph attention networks model, which was employed to analyze the graphs and to make the MRI related decisions. We had made use of a technique called as sort aggregation to actually decide whether a person has to proceed for an MRI or not. Later on, once when a person has been flagged or has been advised to proceed for an MRI, we also created a system for the particular person to upload his MRI scan. For this, we made use of a model, which is a VGG16 based CNN transfer learning model, fine-tuned for classifying specific brain disorders. The system provides a clear prediction of the diagnosed brain disease out of the predefined classes, which we already had. Finally, to execute as whatever I have told so far, we made use of a user-friendly web application. The web application was made use of Streamlit and Gradio on Python. And we basically allow the user to enter his or her medical data, which at the back end was being helped using the Roxy server, Roxy cluster. So over to Prashant, who will be explaining the workflow of the project.
Greetings everyone, myself Prashant from RV College of Engineering. So I will explain the workflow of this project. So this whole project is divided into two parts. The first part, NLP, has two steps. The step one starts with aggregating medical data from multiple healthcare centers. And then we move on to pre-process the data to enhance the data quality and structure. And then we label the medical data using biomedical NER, assigning unique identifiers. So here we assign numbers such as 1, 2, 3, 4 for difficult medical entities like symptoms, diagnosis, and duration. And then we implement BioBERT for generating contextualized embeddings from biomedical texts. So here we took the vectors from BioBERT. And then we researched on advanced deep learning models for efficient medical entity recognition. So using all this, we then trained a custom NER model using conditional random fields, which helps us in getting more context on the PMC dataset we had. So this whole model of the step one process was deployed on HPCC Systems Roxy cluster for the web-based access. And then on this step, we have got all the medical entities. It's time to move on for step two, where we generate specific patient-specific graphs using extracted entities as nodes of the graph for analysis. So here the goal is to check if a patient requires an MRI or not. Then we created mappings for symptom to organ and symptom to duration relationships. So here we developed a graph attention network to predict MRI scan requirements. So this step 2 part was also deployed on the HPCC systems for Roxy cluster to web to access on the web. I will drop the research paper we referred for this. And then this is the part 2 of our project. We collected the MRI scan dataset related to brain disorders. And if a person required the MRI scan, he has to upload the MRI scan and he will get what disease he had. So in this process, we resized and pre-processed the required input size. And then the fine tuning was done to classify the diseases. And we trained model on labeled data set, which has diseases like glioma, pituitary tumors, and Alzheimer's. And on this web application, which encodes image to base64, was passed to Roxy query. And then from Roxy query, we received a JSON response, which was passed, and the model was predicted classes with particular probabilities. Now I will show you some sample outputs of the patient graphs. So this is graph of one of our patient. So this graph had, you can see this has many nodes, and each nodes are interconnected, and the organ node has many branches for the duration and for the symptoms. Now I will show you the demo of our NLP part. So this is our web-based interface done using Streamlit. So here you have to enter the medical text of a patient which you want to assess. So I am pasting here a data of a 63-year-old patient who had respiratory diseases. So when I click on submit, what happens in the background is a query is passed to the Roxy cluster. So what it does is the text is tokenized into different words and then letters, and then the embeddings from the BioBERT are taken, and then they are passed on the BioSTEM CRF model. So this is the response we received from the Roxy cluster. So that is put into Pandas data frame, and this is displayed. So these are the medical entities we got, and using this, we assess if he requires an MRI scan or not. So when I click on predict, we will get if he requires an MRI scan or not. So this part is the second part where the graphs are created. So here you can see he requires an MRI scan. So now Nikhil will present the second part of the project.
Hello, everybody. I'm Nikhil Vasu, second year computer science engineering at RVC. I'm now going to be demonstrating the second part of the project, which is an MRI scan classification. So this is the front end we have developed using Python Gradio. So right now we will be showing how to classify tumor patients. So there are 4 classes: glioma, meningioma, pituitary, and no tumor. And I will now be uploading an image. So this is a patient who has been tested positive for pituitary. So what happens here is the image which the patient has uploaded is basically encoded as a base64 string. This is then passed into the Roxy query, which is processing it in the backend, and we receive a JSON response from the Roxy, and we'll be able to see the predicted class with the probability. So I will now submit the image. So here you can see that we received the JSON response from the Roxy cluster, and the predicted class is pituitary as it was, with a probability of 95.95. So I will now demonstrate another image. So right now I'm going to restart the cluster. So now I'm going to upload another image. So this time I'm going to add a no tumor patient. So this is a normal brain scan. And now I'm going to click on submit. So here you can see that the predicted class was correct with almost 100% accuracy. So the model performs well. So we use a CNN-based transfer learning model here. So this is my demonstration. Thank you. So now I'll be speaking about how we leverage the HPCC Systems platform. As we know, medical data is highly unstructured and requires a lot of pre-processing. So the better we process this data, the better our model performs. So we are fortunate enough to leverage the HPCC Systems distributed computing platform, which significantly enhances our computational capabilities. So here we input large medical texts, which are efficiently divided and distributed across multiple nodes within the cluster. Each node processes its portion of the data independently, allowing computations to occur in parallel. This not only accelerates the pre-processing in this project, but also enables us to handle many queries that would be challenging to manage on a single machine. By distributing both the data and the computational load, the HPCC systems technology ensures faster processing times, better resource utilization, and the ability to scale as the data volumes grow. We have utilized the Roxy cluster of HPCC systems for several key tasks here. First, we deployed our .pth file, which is a binary file, onto the Roxy cluster, enabling it to generate outputs whenever required. When a medical text is entered, the entire pre-processing occurs on the system, leveraging the distributed computing power. The Roxy then returns a table which is populated with the extracted medical entities. In addition to this, it also provides JSON endpoints, allowing us to connect it seamlessly to our custom website as an API, which enables quick and efficient responses to queries, giving us a seamless integration and a smooth user experience. By using this Roxy, we benefit from fast, reliable, and scalable processing that are essential for handling complex medical data analysis. By dividing the MRI data and tasks across multiple nodes, we were able to use the parallel processing capability and accelerate both the data handling as well as the model training. We used a VGG-based convolution neural network and a transfer learning model, which enabled us to manage large data sets and complex computations, leading us to faster training and better performance. This was deployed on the HPCC systems via a dedicated API that integrated with our web application. So the HPCC system technology ensures reliable, fast processing, crucial for analyzing complex medical data, and hence improved our system's efficiency and accuracy. So these are our reference papers, and below is the links for our GitHub, which contains the code for our project. That will be the end of my demonstration. Thank you. I will be handing it over to Ifan.
Hello everyone, I'm Yifan Wang. I'm an assistant professor from University of Hawaii. So today I will talk about learning cache size setting for Roxy clusters. So first is a brief introduction to myself. Currently, I'm an assistant professor in the Information and Computer Sciences Department at University of Hawaii. My research area includes AI for database, database for AI, and vector databases. And currently, I have collaboration with the HPCC systems on learn cache size setting for Roxy clusters. Let's first talk about the Roxy. Roxy system or Roxy cluster is a fast query engine to retrieve data stored in HPCC systems. So it provides efficient index structures to make sure it can access the data in a fast manner. And furthermore, it also designed an internal cache to cache the recent data and such that it can speed up the frequent queries furthermore. And our goal is to detect, to predict the optimal internal cache size. So the current issue is it is hard to do that because of the competition between the internal cache size and the OS operating system page cache. So in Linux, there is a page cache which is used to cache the frequent data read from disk. And this page cache will have to compete with Roxy's internal cache on the memory because they are sharing the same memory. So the page cache, because it stores data directly read from disk, so the data there is compressed data. Therefore, the data is smaller. The page cache can store more data, but it has to decompress data before use. Therefore, it will need more time. And the internal cache, it is used to store decompressed data. So the data will be larger, it can store less data, but also it will need less time because there's no decompression. And our goal, what we want is we want more data stored in memory instead of disk because read from disk is much slower. Also, we want less decompression time. We want less latency. So we can see there is a trade-off between more data or less time. And therefore, we have to trade off between the size of page cache and size of internal cache. That's why we have to have a way to find optimal internal cache size. But this is difficult because there are too many factors will impact the overall latency in addition to the page cache and internal cache themselves, like the memory limit, like the compression ratio. For example, a compression ratio of 10% versus 90%, it will be definitely different because it will determine how much more data that page cache can store comparing to internal cache. And the disk I/O, let's say extremely, if the disk have a fast speed as the memory, then there is no need for using any cache. And also the query distribution or query frequency on the data. So there are too many factors that will impact the selection of the cache size. So it is not an easy issue. So for this project, we propose such a method, which has two parts. The first part is simulation, and the second part, which is also the core, is the machine learning to predict the best cache size. So when we have a simulation, that is for collecting the training data to train the model. We will introduce the simulation part later. First, let's talk about the learning model, which is the core of the method. So our goal is to predict the best internal cache size under different system parameters, as well as different queries. So this is belong to a very hot topic, which is called knob tuning in database area. So the database has a lot of configurable knob, like buffer size, like the number of maximum connections, like many things else. They can be configured and how to find the best setting for those parameters for these knobs. It has been studied for a very long history in database area. And so one of the popular methods is Bayesian optimization based method. It's trying to learn a probabilistic model by Bayesian optimization. And this model can map the relationship from configuration to the database performance. So we can select the best configuration from this model. But this only works well with small number of embedding factors because it is a probabilistic model. It is not that deep, so it cannot work well on a large number of embedding factors. Therefore, the state-of-the-art method is deep learning method. And our proposed method is also around a deep learning model, which is essentially a neural network. We will conduct our model based on one of our reference. And here is their architecture in the reference. And we will briefly introduce how they build their pipeline and how we plan to improve it. So in the pipeline, first, that's the database configuration and the data processing. Then the processed data from the database will be fed to the pre-trained model, and the model will predict the best cache size. So BP size is the cache size, and the predicted running time by using this kind of setting. If the predicted time is acceptable, let's say lower than some threshold, then it will be input to the executor to do the real execution and check the execution time. If the execution time is really good, then it means that the predicted cache size is okay, and then the database will be configured as it and then just use it for future work. But if the time is actually longer than previous one or than threshold, it means we have a bad prediction, and this will be fed back to the database. And the database may decide to roll back to the last optimal cache size setting. So this is their overall workflow. And on our side, we will make some innovation to improve the model. Like we will try to add the incremental training for the model. So let's say here, in addition to feedback to the database configuration, we will also feedback the real execution results to the model. So the model can be updated online. And let's say if the prediction is bad, then the neural network may be trained to avoid this kind of prediction. So by this incremental training, it can be trained faster without have a very long downtime to train it offline. And we will also try to speed up the training and prediction of the prediction model. That is also for the purpose that we do not want that long system offline time. We want to select the best configuration as fast as possible. So that's why we will try to speed up the training prediction, and this is under specific constraints because we do not want to waste too many hardware resources on the network training or prediction. We want to leave more resources to the user storage, user's query, this kind of things. So this will be another innovation of us, and we will have many other innovations, and I will not talk too much here. Then we talk about how to train the data. So to train to train the model, the first important thing is the data. Here we show how the training data will look like. So it includes three parts. The first part is the cache size, and the second part, F1, F2, there are other system parameters like the current memory limits, like the disk I/O speeds, like the compression ratio. And the final part is a query embedding, which is we input the data access query to some other deep learning model, and the model will generate an embedding, which is a numeric vector represent the query. So by using such a kind of embedding, the query can be represented in a numeric way, which is much easier for our learning model to learn. So we will vary the cache size, we will vary the system parameters, and we will vary the query in this training data. Then we will have a lot of training vectors. So we will feed that into the learning model to learn the distribution of those feature vectors. And we will also need a training label. The training label is simply the retrieval latency or the internal execution cost. So like in many databases, there will be the internal cost, which is not necessarily the latency, but some numerical cost to estimate how long the query will be executed. And let's recall this. We have a simulation part in our method. And this simulation is to collect the data. So that here's why. Because there is problem in data collection. We do not have real training data. In our collaboration with HPCC, the Roxy cluster, it is hard to be frequently restarted and try the different parameters and try different queries to get the real response time in the real environment. So that's why we want to use a simulation to get the training data, because we don't have the real training data. To make it, we will have to simulate a simplified Roxy cluster. So first, the most important part is simulate an internal cache and page cache. As we mentioned before, the internal cache, it stores the decompressed data in memory. And the page cache, it stores the compressed data in memory. So it's not only simulate the cache, but also simulate the compression ratio and the decompressing time, as well as how the compressed data is stored in the disk. And next part would be index structure. So usually it's a B-tree structure, and we have to simulate it because it is the core part in Roxy cluster, in Roxy engine. And the disk I/O, it is another very important factor. So if the data is in neither internal cache or page cache, it has to be read from the disk. At this point, the disk I/O is very, very important. It will heavily impact the overall latency. So we have to simulate it also. And like I mentioned, we also have to simulate the data compression. So here is a workflow for the simulation. It is a simplified Roxy workflow. So like the query income. So first we will check whether the data is in internal cache. If yes, directly search the data in memory. Otherwise, next step is to query whether the data is in page cache. If yes, read it from page cache and decompress it, then search. Otherwise, we will have to read the data from disk and also decompress and get the data. So this is a very simplified version of the Roxy, and actually our simulation will not be as simple as this one. This is just a figure for better understanding. So of course, the simulation will include many other details inside it, like the how to simulate the different query distribution, how to simulate the data location stored in the disk, like this. There would be a lot of there would be many more factors, many more things to consider in the simulation. Of course, it is not as complex as the real Roxy systems. And the input to the simulation would be varying system parameters and varying queries. And the output would be approximation of the real-world response time or the real-world internal cost in Roxy cluster. And we will try to make the approximation as close as the ground truth response time. So this would be the metric for measuring the simulation accuracy. And once we have a accurate simulation, we have the accurate simulation results, then we can use it to train and evaluate our deep learning model. So we will still have some real world data from Roxy cluster, which will be provided by HPCC Systems, but a large portion of the other we will have a large data set to train a deep learning model. So a large portion will be from the approximation. So yeah, as I mentioned, the data set would include the simulation results, which is the biggest portion, and a small portion of real performance data from Roxy. And the evaluation metrics would include mainly three things. The first one is cache missing rates. Is when we set the cache as our predicted cache size, and the response time with the predicted cache size, and the memory usage. So we do not want the cache size to be too big, or it exceeded memory. Yeah, and this my reference. And thank you for listening, and thank you for joining us in HPCC Summit Talk 2024. I'm so happy for you to join listening. Thank you.